It's okay lah. While waiting for the recording to start, we can continue with the revision first. Okay, it's already started. All right. So let's continue. Okay. So for first center tap full wave rectifier, the peak value of the output, the peak value of the output is the secondary. Okay, the secondary. This is the secondary. The peak at the secondary part is divided into 2. Okay, because some of the voltage will flow here, some of the voltage will flow here. That's why it divides into 2. And then 0.7 minus 0.7, because if the voltage flow here, one of the diode will be reverse diode. Okay, reverse bias diode. One of the diode will be forward bias diode. So the reverse bias diode will gonna be off, right? And the forward bias diode will be on, right? So that's why it will minus only one value of the diode drops. Okay, so minus 0.7 volts. Okay, same as half wave rectifier. The value also will be depending on what types of the diode is used. Yeah, so sometimes the value of diode drop will be given to you. So it depends. If they mention that VD is equal to 0.6, so this value should minus with 0.6. Okay. And then the average value of output. Okay, so average value 2 times with the output peak. Okay, output peak waveform divide into pi. So this is different with the half wave rectifier. Okay, half wave rectifier, there's no multiply with 2. But for full wave rectifier, for center tap, you should multiply by 2. Yeah. So the diode peak inverse voltage will be PIV equals to 2 VP output, the value of the peak at the output, plus 0.7. Yeah. So this is the peak inverse voltage. And you also should take note about the patterns of the waveform. Yeah. For the half wave rectifier, okay, half wave rectifier, it will block of the minus voltage. So there will be no currents, or there will be no voltage at the minus region of the input voltage. Yeah, only they will transfer the positive region of the input voltage. Right. So for the center tap full wave rectifier, okay, the waveform will looks like this. Yeah. Okay, it will transmit both of the positive and the negative region of the input voltage source. Yeah. Next is the bridge full wave rectifier. Okay, for bridge full wave rectifier, the peak value of the output is VP secondary, V peak at the secondary value, minus 1.4 volts. Why it is 1.4? Because it will turns on two diodes. Okay. For example, when the voltage is, the input of the voltage is positive region, these two diode will on. Okay, it will on. So it will plus 0.7, 0.7 will be 1.4. So if this value of diode voltage is 0.6, so 0.6, 0.6 are going to be 1.2. Okay, so it will not always 1.4. It depends on what kind of, same as previous, it depends on what kind of diode it has been used. Yeah, so be careful of this value. Okay, and then average value of output, same with center tap. Okay, so the average formula is same with center tap full wave rectifier here. And the diode peak inverse voltage, so V peak output plus 0.7 volts. Okay, and the waveform same with center tap operation full wave rectifier waveform. Okay, so this is just the summary of our previous lesson. So for today, we will learn about voltage regulator. So what is a voltage regulator? Okay, it maintains, voltage regulator, the main job is to maintain a constant DC voltage. Okay, as we have know, yeah, the input voltage usually it is in a AC, okay, AC form, okay, AC form. So since it will it will undergo to transformer, okay, transformer will um, uh, 2 to 1 or 1 to 2, okay, will increase the value or decrease the value of the voltage source of AC voltage source, right? Then, then diode rectifier, okay, diode rectifier will rectify the voltage, okay, will allow the voltage to be half wave, okay, half wave or full wave, okay. It will allow the AC voltage turn into DC, okay, only one direction. And then filter will filter the noise, okay, will filter the noise that we have learned before, the ripple, okay. So it depends on the filter. And then today we will learn about what is the voltage regulator. So voltage regulator, it will maintain a constant DC voltage or current, okay, for variations in the input line voltage or in the loop. Okay, it will maintain the constant DC voltage. Okay, it connected to the output of the filtered rectifier. Okay, the combination of large capacitor and a voltage regulator helps produce an excellent power supply. All right, so the voltage regulator will make sure, okay, after the voltage or the current has been filtered, it will decrease, yeah, the ripple better. It will make sure that you see here, it will make sure, okay, the output wave, yeah, will be as smooth as possible. Okay, so it contains 3 terminals. It have input terminals, output terminals, and reference or adjust terminals. Okay, so if a circuit, yeah, without a voltage regulator, only a filter, there is a possibility, okay, that there is still noise contains inside the waveform. All right. So voltage regulator is useful to make sure that the noise after the wave has been filtered to be completely eliminates. Yeah. So this is the example of a voltage regulator. Yeah, the input from the rectifier. Okay, so the input waveform from the rectifier, okay, will undergo the capacitor, where the capacitor will decrease. Yeah, will reduce the input ripple to less than 10%. Okay, after that will goes to voltage regulator, where voltage regulator will reduce the ripple to the negligible amount until it is not exist anymore, yeah, as maximum as possible. And then it will goes into output, yeah. And there's also another capacitor here, which is external capacitor to complete the regulation portion of power supply. Okay, so most regulators, yeah, have an internal voltage reference, short circuit protection, and thermal shutdown circuitry. Okay, they have usually, yeah, they have voltage reference. They has also short circuit protection, protection, and then they also have thermal shutdown circuit. Okay, and voltage regulator are available in variety of voltages, including positive and negative output, and it can be designed for variable outputs with a minimum of external components. So this is just extra knowledge of voltage regulator. Okay, so we will see, okay, for voltage regulator, okay, how to calculate the percent regulation, the number of percent for regulation. Yeah, so regulation expressed as percentage is figure of merit. So what is figure of merit? Figure of merit ni usually to express something, okay, something to express formally. For example, figure of merit for for loss. For example, figure of merit for figure of merit for let's say figure of merit for some device. Okay, you want to calculate the loss, so we will say that the figure of merit of the device is around 4 dB loss. Okay, so this is the standard value to show the loss of this device. So figure of merit ni macam standard standard value ataupun standard amount of to present something. Okay, so figure of merit for to express the percentage of regulation used to specify the performance, used to specify the performance of voltage regulator. And it can be divided into two, which is line or input regulation, or there is also load regulation. So there are two types of percent regulation. It can be line regulation or input regulation, or it can be load regulation. So it depends on the question, what the question asks you. Okay, so for line regulation, it specifies how much change occurs in the output voltage for a given change in input voltage. Okay, so how much change occurs at the output for a given input. Okay, so the formula will be delta output divided by delta input, since that it is percent, so you have to times 100%. So for load regulation, it specify how much change occurs in the output voltage over a certain range of load current values. So usually from minimum current to maximum current. Okay, which is minimum current means that no load at all, and maximum current means that full load. So the formula is voltage without load, okay, voltage with no load minus with voltage with full load. Okay, so divide over voltage with full load and times 100%. Okay, so this is the load regulation formula. Okay, so that's all for voltage regulator. So next we're going to look about Zener diode. So what is Zener diode actually? So Zener diode, okay, is a heavily doped diode to reduce the breakdown voltage. Okay, and it has a very thin depletion region. Okay, so for Zener diode, the depletion region is very, very small. It's very, very thin, very, very narrow. Okay, so it is very high, heavily doped. The amount of dope for Zener diode is very high because it's to reduce the breakdown voltage. So it operates in reverse breakdown. Okay, so different with usual diode. Okay, usual diode operates in forward bias, right? When reverse bias, usually for normal diode will be off, right? Conditions. However, for Zener diode, it is designed specifically to work in reverse breakdown. Okay, it works in minus voltage, it reverse current. Okay, so mainly used for voltage regulation. Okay, so voltage regulator that we have that I mentioned just now usually contain Zener diode. Okay, and to limiting application. So that is the function of Zener diode. In reverse bias condition, the Zener diode is on, and the voltage across the diode is called Zener voltage. That's why there is a Z here, which represents the words of Zener. Okay, VZ usually. Okay, so in forward bias, Zener diode act like the regular diode. Okay, act like the regular diode, which is it is off. So so this is the image of the Zener diode. Okay, Maybe some of you have seen this before. Okay, and this is the symbol of a Zener diode. Yes, you can see that if normal diode, it is straight, right? But for Zener diode, behind here it looks like Z because it represents Zener. Okay, so anode, okay, and then cathode. Okay, and then the direction of the current flow is different between Zener and regular diode. Okay, so Zener diode, the direction of the currents is from cathode to anode, but regular diode from anode to cathode. Okay, so the direction of current flow is different in Zener diode. Okay. Okay, so that is the information about Zener diode. Yeah. So for forward bias, a Zener diode will act like regular diode, same as regular diode for forward bias. Yeah, it will not called as Zener diode anymore. Okay, if it is forward bias. So Zener diode is only called when we apply reverse bias to the Zener diode and it is on. Okay, and the diode is on, so that's only that we call the diode is Zener diode. Okay.
Sensei. Sensei.
Yeah, yes.
Maksudnya kalau yang Zener diode ni, kalau forward bias dengan reverse bias dia akan still function lah.
Yes,
Maksudnya
yes.
kalau forward dia takkan off. Macam tu.
Yes. Betul. Dia takkan off. Maksudnya the current direction will be different. In a forward bias, the current direction will be the other way around. Macam normal diode.
Okay.
Okay. But in that condition, kita tak panggil, we didn't call the diode as Zener diode. Okay, we called it as normal diode. Okay.
Oh, maksudnya kalau kita change the voltage direction baru kita panggil the Zener.
Yes. Sebab usually at minus direction, at reverse bias, usually the diode is off, right? For regular diode, okay? But for Zener, it is on. So that's why we call it Zener diode. Okay?
Okay.
Alright. Yeah, I want to check. Sometimes I need to check the comment too. I didn't look at the comments. Okay. Alright. Next. Okay, so this is a Zener diode for the Zener breakdown. Okay, so Zener breakdown occurs in Zener diode at low reverse voltage. Okay, and the breakdown voltage less than 5 volts. Usually, the breakdown voltage is less than 5 volts. The breakdown voltage is set by carefully controlling the doping level. Okay, so if you want to create a Zener diode, you should control the doping level. Okay, so if you at certain point of doping level, okay, at certain point of the doping level, the currents can flow at the after the breakdown voltage. So it will create Zener diode lah on that condition. Yeah, in that condition. So the reverse current also called as Zener current. Yeah, the reverse current also called as Zener current. So it will represent as IZ. Okay, the internal Zener resistance decrease when the reverse current increase rapidly. Okay, so you can look into this graph. Yeah, so the reverse breakdown region is normal operating region for Zener diode. So at this region, is the normal operating region for Zener diode. So Zener diode is operate at this region after the breakdown voltage. Okay, at this region, Zener diode will operate. So at this region, you can see if with the small changes of voltage of reverse voltage, okay, small changes of reverse voltage will produce a large currents. Okay, for example, at this voltage here, the current is at this point, right? But at this voltage, the current at this point. So you can see the changes of voltage. The changes of voltage is very small, but the changes of current is very big. So that's why when you increase the reverse voltage, okay, it will decrease as well the impedance, the resistance inside the Zener, because currents can flow the currents can flow rapidly, even though the changes of voltage is very, very small. Okay. So it means that the resistance is decreasing when the reverse current increase rapidly, right? So VZ here, okay, VZ here represents to Zener voltage, okay. IZ here, itu tadi IZ, okay. So usually IZ represent to Zener current, okay. VR represents to reverse voltage, VF forward voltage, IF forward current, IR forward reverse current, okay. Okay, next. Yeah. So IZ, the Zener current must be large enough to put the diode into breakdown. Okay, IZ must be large enough to put the diode into breakdown, which is IZ should be bigger than IZK. What is IZK? IZK is Zener knee current. Okay, Zener knee current. It is at this knee breakdown kan. Kalau kita belajar in normal diode, okay, this we call knee breakdown, kan, knee voltage, knee breakdown, okay. But for Zener current, for Zener diode, this IZ, the IZ that flow inside the Zener, the currents that flow inside the Zener should be bigger than Zener knee current. However, it shouldn't be more than Zener maximum current, okay. Even though Zener diode works at the breakdown region, but it has limitations. It cannot be too high, the voltage. It has a limitation. At certain point, okay, at certain point, the Zener diode can be broken. Yeah, so the voltage cannot be more than Zener maximum current. Okay, so you should control the voltage not more than this value. Okay, more than this value, the Zener will break. Yeah. So breakdown effect begins at the knee point. Okay, so this is a previous lesson. Yeah, breakdown effect begins at the knee point. So if IZ lesser than IZK, okay, lesser than I knee current, Zener knee current, the Zener acts as regular diode. Okay, which is at this region. Okay, regular diode is off condition, right? Off condition. So it is off and it is assumed as open circuit. However, if the IZ, okay, currents inside Zener more than Zener knee current, okay, exceed Zener knee current, okay, so the Zener diode will on, okay, at this region, Zener diode will on, and we assume the circuit, we call the circuit is closed circuit. Okay, so the limitation, the limitation or the range of Zener current should be more than Zener knee current, and lesser than Zener maximum current, cannot more than Zener maximum current. Okay, so this range. Okay, so Zener diode maintains nearly constant voltage. Okay, so usually the voltage range is very small. Okay, the voltage reverse voltage range is very small, but it will produce a lots of currents. Yeah, so that's why Zener diode maintains nearly constant voltage, and this is what we call Zener regulation. Okay, Zener regulation, because the voltage changes is very small. Okay, and it is constant. Okay, the voltage range is constant, and that's why Zener can be used inside the voltage regulator. Okay. Okay. So IZK, what is IZK? IZK is a minimum value for IR, which is reverse current, to keep the diode in breakdown region. Okay. And then IZT. IZT represents to Zener test current, where at this value, a nominal VZT, which is voltage Zener test, voltage Zener test is specified on a data sheet. And then IZM is the maximum current above which the diode may be damaged due to excessive power dissipation. Yeah. excessive to power dissipation. So you can see Zener test current, usually we will take in the middle between Zener knee current and Zener maximum current. Okay, the reason why we didn't take Zener test current at this point, because because you can see at this point, okay, the changes of the currents, the changes of the currents is too rapid. Okay, the changes of the currents is too rapid compared to here. Compared to here, you can see that the changes of the currents is gradually increase, but from here is too rapid, too sudden, the changes of the current. Okay, so we cannot take the Zener test current at this point. Usually we will take at the middle between the Zener knee and Zener maximum. Okay. So here is the difference between regular diode versus Zener diode. Okay, so for regular diode, so this is for regular diode, it can be separated into three regions. Forward bias, where it will conduct the current. Okay, reverse bias, okay, it will block the current. Okay, at the breakdown, okay, so the graph will look like this, right? The graph will look like this, kan? Okay, so at this is reverse bias, it will block down the current. But for the breakdown region, the diode usually overheat and damage, right? So that is what will happen in regular diode. So regular diode is manufactured, okay, it's specifically designed to work at forward region only. But for Zener diode, what will happen? Okay, what will happen at this stage? We will call it as, it will operate as regular diode. Okay, regular diode, where it will conduct current as usual, like forward bias. At this stage, it will off. It will off because the Zener current is not as more than the Zener knee current, right? So it is off condition. So at breakdown, which is here, at this point, breakdown region, it will on. Okay, with the limitation of IZM, Zener maximum current. Okay, so Zener diode is designed specifically to work well in the breakdown region. In a breakdown region. So this is the comparison between the regular diode versus the Zener diode. So at this stage, we call the black circle. Is a regular diode operating region. Okay, which is a forward bias. Okay, forward bias region, forward bias diode region. At this state, both regular diode and Zener diode will off. Okay, and at this state, the red circle, the Zener diode start to operate. So you can see the value for silicon and germanium usually different, the value, and same with the forward bias too. The germanium usually the value is 0.3. For silicon usually is 0.7. Okay, so I think these two value you already know. Okay, so here are the dark current. Okay, value for germanium usually 10 nanoampere and silicon usually 0.01 microampere, lesser than germanium. Okay. Okay, now let's look into Zener equivalent circuits. Okay, the circuits of the Zener for Zener diode. Okay, first of all, as previous, we know there are three models, right? Ideal model, practical model, and complete model. So for Zener diode, we will look into only two types. Okay, ideal model, and another thing is practical model. Okay, practical model. So for ideal model, it's very easy. Okay, it has constant voltage drop equal to nominal Zener voltage. What is nominal means? Nominal is very, very small. Okay, the meaning of nominal is very small Zener voltage. Okay, so we will say that inside Zener, okay, inside Zener diode, there is no there is no impedance, there is no resistance at all. We assume that there is no resistance at all. So the current, the current is like this straight current, Zener diode does not produce a voltage. Okay, it will not. We will say that Zener diode doesn't have any voltage inside that. So the current is the current is maintained at one stage of voltage. Right. So this is at the ideal model. So let's look in a practical model. Okay, so practical model usually will be asked in your questions. Will ask usually at practical model, because at practical model there is a value of a Zener voltage. Okay, so you can see ZZ here. ZZ here, Z represents into impedance. Okay, impedance also known as resistance. Okay, impedance also known as resistance, also called as resistance. So in a practical model, there is Zener impedance or Zener resistance included. Okay, and a small change in Zener current, okay, usually delta IZ, produce a small change in Zener voltage, which is delta VZ. So in order for you to calculate the value of impedance, we know this is come from the Ohm's law, which is V equals to I R. Okay, R is impedance. So in order for you to measure or calculate the impedance value, so R or Z, or Z is V over I. So here comes the formula. So ZZ equals to delta VZ over delta IZ. So the changes of currents at this point to this point, the changes of voltage from this point to this point. Okay, and if you want to calculate the impedance value for the Zener, it is best for you to avoid at this point. Okay, at this point, at this region. Okay, because as I mentioned just now, at this region, the currents, changes very dramatic, very great, very rapid at this region compared to this region. You can see that the currents, changes very increase with constantly increasing compared to at this point. The currents move too rapid. So usually, if you want to calculate the impedance, try to take at the point of in the middle between the Zener knee and Zener maximum. Okay, so this is the best area. In the middle is at the middle between Zener knee and Zener maximum is the best area. So here are the example. Okay, for example, question: a Zener diode exhibits a certain change in VZ for a certain change in IZ on a portion of the linear characteristics curve between Zener knee current and Zener maximum current as illustrated below. So what is the Zener impedance? So they ask, what is the Zener impedance? They already give to you the changes of voltage and current value. So it's very straightforward for you to measure the impedance value. Just divide the voltage divide by the current, and it will give you 10 ohm around that. Next, let's look into Zener power. Okay, so for Zener diode 2, you can calculate the power. Okay, so the power can be divided into two, which is dissipation and derating. So what are the difference between dissipation and derating? Dissipation is a maximum DC power dissipation, maximum power, maximum specified power to operate the Zener diodes. So to calculate power, usually P times IV or IR, right? I squared R. Okay, so usually for you to calculate power, this is the formula. So for Zener diodes, yeah, to calculate the PD, power dissipation, VZ, yeah, V voltage of the Zener times currents of the Zener. So if the voltage of the Zener is not given, but the impedance of the Zener is given, so you can also change this formula into PD equals to IZ squared times ZZ. Okay, if the impedance of the Zener is given. Okay, sometimes in your questions, this is also represent as R. Yeah, they will mention the resistance of the Zener. Okay, R symbolized as R2. So don't be confused. It is just same. Okay, so the derating Zener power for derating is the maximum power dissipation of a Zener diode specified for temperatures. Okay, for derating there is influence of temperatures. Okay, at or below a certain value. Okay, so for derating there is influence of temperatures included. Okay, so above the specified temperatures, yeah, the maximum power dissipation is reduced according to a derating factor. Okay, so Zener diode, yeah, is limited by, also will be limited by the temperatures. Okay, so the power, yeah, the power, if we, well, biologically, if the VZ increasing, IZ will increase, PD will increase too, right? However, at a certain stage, when VZ is increased, okay, VZ increase, the power inside the Zener, the temperature inside the Zener will increase too. Okay, the temperature inside the Zener will increase too, and you have to take this into account. Okay? You have to consider this value too. So it will not increase the power dissipation. Okay, the power will not increase because the temperatures increase. So since that the temperature increase, it will decrease the power. It will derate the power. Okay, so this is what we call derating factor. Okay, so PD maximum. Okay, PD maximum should minus with the temperature coefficient. Okay, temperature coefficient. So you will get PD derated. Okay, PD derated. Okay, so PD is VZ IZ, okay, minus with this amount. Yeah, this amount usually is given to you. Okay, MW over milliwatt over changes of degrees. Okay, so this value is usually given to you. So we can look here. This is an example of the equations. Okay, a certain Zener diode has a maximum power rating of 400 milliwatt. Okay, this is the maximum power rating, 400 milliwatt at 50 degrees Celsius, and a derating factor of, this is the derating factor of 3.2 milliwatt over degree Celsius. Determine the maximum power. Okay, what is the maximum power the Zener can dissipate at temperature of 90 degrees? Okay, so if you want to calculate, okay, so this is the solution. Okay, so PD maximum is already given to you. Yeah, maximum power rating is 400 milliwatt, and this value of derating factor also has been given to you, which is 3.2 milliwatt over degree Celsius. So just write the value. And then what is the delta T, the changes of the temperature? So the question asks the maximum power the Zener can dissipate at the temperature of 90 degrees, right? So 90 degrees minus with the maximum power at 50 degrees. Yeah? 90 minus 50, so you will get the value is 40. Yeah, 40 and times with 3.2 will give you this value, and you will get the answer for PD derated is 272 milliwatt. Okay, always remember power. For power, the unit is milliwatt. Okay. So this is the example of Zener diode data sheets. Yeah, usually if you buy a Zener diode in any store, hardware store, it will comes together with you a data sheet. Okay, a data sheet. So this is the example of data sheet for Zener diode. Okay, so this is the data sheet for 1N4728 to 1N4764A, which is, this is the series of Zener diode. Okay, a series of Zener diode for 1 watt. Yeah. So IR here. Yeah, IR is the values of VR, which is reverse voltage, lesser than knee voltage. Yeah, and sometimes manufacturers will give you current Zener current maximum rather than power dissipation maximum. Okay, so it depends. Yeah, sometimes they will give you the value of IZ max, sometimes they will give you PD max. So based on this data sheet, if they given to you IZ max, you can calculate the PD max, right? Use this formula. But if they are given to you PD max, you can also find the value of IZ max given with this formula. Okay, so if you have data sheets, yeah, if happen to be, if you buy a Zener diode later on, okay, try to look at the data sheets, okay, and try to look at what information are given to you, and you can always find the other information as well based on the data sheets. Okay. All right, so let's look some example here. So the maximum power dissipation, PD, is specified as 1 watt up to 50 degrees Celsius. Generally, the Zener diode should be operated at least 20% below this maximum to assure the reliability and longer life. Okay, so this is maximum. Usually it is operated less, at least 20% below with this value. Okay, to make sure its reliability and its longer life. So the power dissipation is derated as shown on the data sheet at 6.6 milliwatt for each degree above 50 degrees Celsius. The maximum power dissipation, so you can calculate the maximum power dissipation at 60 degrees. Let's say the Zener diode is worked at 60 degrees Celsius. So what are the value of power dissipation? So 1 watt, the maximum value of power dissipation, 1 watt minus with the value of power is given to you too, 6.67, power dissipation derated value, 6.67, and then times with the changes of degrees, 60 minus 50, 60 minus 50. So it will give to you that the PD, power dissipation at 60 degrees, almost approximately 1 watt. Okay, for at 60 degrees, approximately the power dissipation for the Zener diode is 1 watt. However, if you increase the temperature value, what is the value of the power dissipation? It will be lesser, okay, which is 0.4, which is approximately 0.5 watt. So you can see if the temperatures it becomes higher, okay, if the temperature is higher, the power dissipation become lesser, okay, because there is a limiting of the Zener diode. If it is too high the temperature, it will lower the power of the Zener. So a maximum reverse current is not specified but can be determined from the maximum power dissipation for a given value of Vz, right? So at 50 degrees Celsius, the maximum Zener current for a Zener voltage of 3.3 volts is, so this is given to you, right? Vz is given to you, which is 3.3 volts. PD also is given to you, which is 1 watt. So you can calculate what is the maximum of Zener currents. So 1 watt divided by 3.3 volts, it will give you 303 milliampere. Okay. I hope up until now is okay. Is it okay up until now? Okay, jap tuan-tuan. I just read the comment. What is the function of Zener diode? Dia control temperature, tak bagi dia overheat ke? No, the function of the Zener diode is to control for voltage regulation. For voltage regulation, it controls the voltage regulation just now. Okay, as I mentioned in voltage regulation, we have earlier kan, I mentioned about voltage regulator. So the function of voltage regulator ni to make sure that it maintain the DC voltage. So the device will maintain the voltage at certain level. So that is the function of Zener diode to maintain the voltage at certain level. Okay, so at certain level, if the voltage is maintained, at certain level, if the voltage is maintained, so the device, the input to the device, okay, it means that the input of the device have stable input voltage. Okay, kalau voltage level apa nak cakap ni? If the voltage input to the device, okay, is stable, it means that the device can works stable. But if the input voltage of the device is not stable, okay, without voltage regulator, the voltage input of the device will not stable. So it means that the device will sometimes working, sometimes not working because of the input of the voltage is not stable. You have to remember, all this function, all this voltage regulator, filter, rectifier that we have learned, this is all inside the DC power supply. Okay, DC power supply, where is the location of DC power supply? The location of DC power supply is located before currents or voltage enter into your circuit device, electric device. That is the function of DC power supply, to make sure that the wall, okay, sometimes kan kita nak, if you want to on a device, you have to plug in kan the DC power supply to the wall socket, right? So the wall socket usually is, in terms the voltage, is AC voltage. So that's why the DC power supply will change the AC voltage into DC, and then inside the DC power supply there are also other function of electronics, which is rectifier to rectify, to change the AC into DC, and then filter to filter the noise after the changes. Okay, and then voltage regulator to make sure that the voltage supply to the device is maintained. So this is the function of voltage regulator. Okay, so Zener diode is included inside the voltage regulator. So to make sure that, because if you see the Zener diode just now function at a constant voltage, the changes of the voltage for Zener diode is very small. Okay, with the changes of the voltage is very small, it will produce a lots of currents, right? So that's why Zener diodes can be included inside the voltage regulator. So it will make sure that the voltage is operate only that region only, because if it is more, it will make the Zener diode break down. If it is less, it will make the Zener diode will not be operated, right? So it will so Zener diode is to control the voltage itself, right? Is that okay, Cik Heng? Oh, Fahmi. So 20% is just for general knowledge, not used in calculation. Yes, 20% is just for general knowledge, usually. Okay, generally. Control the voltage, as if the voltage is too high, it reduce the voltage curve. As if the voltage is too high, it reduce the voltage curve. No, wait, okay. Go. For example, just now, how the Zener diode control the voltage? You can see here, Zener diode, okay, Zener diode, how it will control the voltage. Usually, in a circuit, if you input a Zener diode, it means that the Zener diode will operate, is set to operate only to work at this voltage. Okay, Zener diode is set to work only at this certain value of voltage. If you see this small changes, the voltage here is very small. It looks like bigger here. It's actually very, very small. It's around, the changes of the voltage is around 0 point something to 0 point something. So the changes of voltage is very small, but it will allow the currents to flow it will allow currents to flow many currents. It will allow lots of current to flow inside the circuit. That is the function of Zener diodes. Yeah, it works at the very small changes of a voltage, but currents can flow freely at this region at the small changes of voltage. So that's how Zener diode works. Okay, but in the condition of reverse bias lah. That's the unique of Zener diode. Controls the operating voltage in that small. Yes, so Zener diode controls the operating voltage in that small range only. Okay, if the voltage is lesser than that value, the Zener diode will not operate. So if the voltage bigger than that value, the Zener diode will break. Okay, so usually inside the circuit, together with the Zener diode, we will apply a resistor to protect this Zener diode, so that the voltage is not maximum, to make sure that the Zener diode will not be broke. So we will look later. Together with Zener diode, there is a resistor. Okay, so there is variety kind of resistor, which is variable resistor and fixed resistor. So Zener diode will not operate alone. It will operate with resistor to control the current. Okay, to control the voltage or currents. Okay, go. Thank you. So this is only for the power. Okay. Next. So first we look at the example first, yeah. Before we look into the circuit of Zener diode, usual circuit of Zener diode. Okay. So from the data sheet 1N4736A. So this is the types of Zener diode. Don't focus on this value. Yeah? So this is the types of Zener diode. Has a ZZ. So this is the impedance value of the Zener, which is 3.5 ohm. So the data sheets give VZ equals to 6.8 volt at a test current, which is IZ of 37 milliampere. So what is the voltage across the Zener terminals? Okay, what is the voltage across the Zener terminal, yeah, VZ, when the current is 50 milliampere? So first, when the current is 50 milliampere. Next, when the current is 25 milliampere. And this figure represents the Zener diode. Okay. So first of all, for IZ equals to 50 milliampere. Okay. When the current of the Zener is 50 milliampere. So the 50 milliampere current is a 13 milliampere increase above the test, which is IZ of 37 milliampere. Okay, so compare. So 37 is a test value, right? So 50 minus 37 will give you 13. So it means that this 50 milliampere is a 13 milliampere increase above the test current. Okay, so delta IZ. Okay, so you can find delta IZ. Delta IZ is IZ minus the test current. Okay, the Zener test current. So 50 minus Zener test current. So it gives you 13 milliampere. So delta V. Okay, delta V is, this is Ohm's law, yeah, IZ, delta IZ times ZZ. So impedance is already given to you. So 13 milliampere times 3.5 ohms. So it will gives you positive 45.5 milliampere. Why it is positive? Because the changes of the currents is increasing the current. Okay, increasing, so it is positive. Okay. So the change in voltage due to increase in current above the IZ value causes the Zener terminal voltage to increase. So the Zener voltage for IZ equals to 50 milliampere is, so VZ is equals to 6.8. Where is it? 6.8? 6.8. Oh, jap. Nanti yang baru join. Okay. So VZ is 6.8 volts, okay, which is data sheet given here, 6.8 volts plus delta VZ. Okay, this is the changes of voltage when the changes of current 13 milliampere. Okay, so you have to plus with the test currents of the voltage. Yeah, so 6.8 plus 45.5 millivolts, yeah, will give you 6.85 volt. So these are the exact value of VZ when the current is 50 milliampere. Okay, so this up until here, this is not the exact value yet, because this is only the changes of current and changes of voltage. Okay, so the exact value is after you plus the changes of voltage with the voltage value at the test current. Okay, so this is the final answer. Okay, so next, let's look when the what is the current, what is the voltage value when the current, when the current is decreasing. Now it's decreasing to 25 milliampere. Okay, just now the test current is 37 milliampere, right? Now the current applied is 25 milliampere. So what are the value of the voltage? So delta Z is minus 12. Why it is minus? It is because decreasing. Okay, it shows that it is decreased. That's why it is minus. Yeah, so minus, how did you get 12? 37 minus 25. So it is minus 12 milliampere. Sorry, there is no Z here. There's no Z here, only milliampere. Yeah? So delta, if you want to find, next you need to find the changes of voltage. So delta VZ equals to changes of current times impedance. So delta VZ, the value is minus 12 milliampere times with the value of the impedance. Okay, value of impedance will always same. Okay, will give you minus 42 millivolts. Okay, so minus means that it is the amount of voltage is decreasing. Okay, so the change in voltage due to the decrease in current below the test current causes the Zener terminal voltage to decrease. Okay, so since the current is decreasing, the voltage will decrease too. Okay, so the Zener voltage for IZ 25 milliampere is, so now 6.8. Okay, 6.8 minus with the changes of voltage just now. So it will gives you 6.76 volts. Okay, I hope this is clear with you. 6.8 is the breakdown voltage. No, 6.8 is the test current. Okay, yeah. I show to you the graph again. This one. Alamak, the test current here. So IZ, at this IZ just now, what is the value? If I'm not mistaken, 3 something kan. So the value of VZ just now is apa tadi? I don't remember. 6 point something. Okay, 6.8. 6.8. And IZM just now is 38 something. So this is IZ is 38 something. So this is the value of test current. Okay, test current. So from this value since that is given, so they ask to you what if the changes of current at this point or at this point. So you need to find what is the value of the voltage. So this is how this is how if you want to find the value of the voltage when the current is 50 milliampere and when the current is 25 milliampere. Is that okay, Ko? Okay. Right. So you always have to compare with the graph that I given to you just now. Yeah, you have to remember the graph lah just now. Okay, this graph. So this is breakdown. This is the IZK. Okay, this is the IZM. ZM maximum. So in the middle, usually IZT, test current. Okay. So if IZT is given to you, you can always, IZT is given to you and the VZ value is given to you and the impedance value is given to you, you can always find the value of voltage or current if one of them is given to you lah. Contoh, for example, if the current is given to you, for example, 50 milliampere, so you can always find the value of voltage. If the voltage is given to you, for example, the voltage value is given at some points, yeah, and they ask to you how to measure the currents, what is the current's value. So it just the other way around from this operation, from this example. Okay. Okay, so maybe after this you can try, yeah, if you want to find value at certain voltage. Okay. Okay, next, let's look into Zener circuit analysis. Okay, so there are types of Zener diode circuit analysis, okay, that you have to know, which is fixed VS. VS means source voltage. Okay, source voltage. So this is for fixed source voltage and also fixed resistor. Okay, resistance load. Okay, resistor. Okay, resistor. So this is both fixed, yeah, the source voltage fixed, the resistor also fixed. Next, another condition, fixed fixed source voltage and also variable load. Okay, so this value, the resistance now is variable. Okay, it's changing. Next, variable VS. So the value of VS now is changing. Okay, it's changing, and fixed resistance value. So this is three conditions that you need to know. Okay, but in exam, if I'm not mistaken, only will come out fixed VS and RL. This is just for knowledge lah, for your knowledge. Okay, voltage regulator. Okay, voltage regulator. A Zener diode can act as a voltage regulator, as I mentioned just now. So it provides a reasonably constant DC level at the output. So we will look how it provides a constant DC level at the output. Okay, so there is RS here. There is RS here. So the function of RS is to limit the Zener current. Okay, to make sure that the Zener current is work in this range. Yeah, it will not limit. It will not exceed or too small rather than this range. Okay, so this is a simple regulator circuit. Okay, this is a simple regulator circuit without any resistance load. But usually, okay, there is a resistance load. Okay, regulator circuit usually comes with load resistance, yeah, to control this VZ. So this load resistance, okay, sometimes it can be fixed, sometimes it can be variable. And this VS2, sometimes it is fixed value and sometimes it is variable value. So we will look into condition, okay, all this condition. Alright, so this is a voltage regulator. Determine the minimum. Okay, this is at the very basic one, yeah, at the very basic one. Determine the minimum V in, okay, V in, and maximum V in. Okay, V in ni, this time, this V in is variable. The voltage source is variable, so it has a V in minimum and V in maximum of input voltage. Okay, how to calculate? For minimum current, IZM. So IZM, minimum current, IZM is equals to PD maximum over VZ. Okay, this is just for your information. This is just for your knowledge lah. When the PD is maximum. PD is maximum. PD is I times V, right? So when PD is maximum, IR, PD is maximum, the current is always minimum. It is opposite way. Okay, when PD maximum, the current is always minimum. So divide with VZ, okay, you will get the value of minimum current. Okay, so the voltage across the 220 resistor is 55 millivolt. Millivolt here. The voltage of VR is equals to 55 millivolts. Okay, so VR, since VR is equals to V in minus VZ, VZ is at the impedance, at the diode, Zener diode. VR is usually V in minus VZ. So V in at a minimum, okay, so this is for minimum, yeah, because the current is minimum. So VR is, you already know, 55 millivolts plus 10 millivolts, because this value is given to you, 10 millivolts. So the minimum input for this voltage is 10.055 volts. Okay. For the maximum, how about for the maximum? So for VR, yeah, VR, IZ maximum value, okay, times R, you will get the value for VR maximum is 22 volts. So therefore, yeah, V in maximum is equals to 22 volts plus 10 volts equals to 32 volts. I think this one you will understand better after I explain this fixed VS and then fixed and others condition too. I think it will be quite confusing if you don't know what is the how to calculate the conditions yet. Yeah. So first we look at the condition first now. Yeah. Okay. So voltage regulator. So how to determine whether the Zener acts as a regulator or not? Okay. So how to determine if first the Zener acts as a regulator or not? So there are 4 conditions that you need to look. Okay. 4 conditions that you need to look. Yeah. First, you need to assume the Zener diode is in an open circuit. Okay, you assume that the Zener diode in open circuit, which means that first you assume that the Zener diode is off. Okay, assume that the Zener diode is off, and then you need to determine the voltage VL voltage across the Zener diode VC. Okay, determine the voltage of VL across the Zener diode VZ, which is, this is the input voltage, right? This is the input voltage. And then there is usually has a resistor here. And then this is a Zener diode. And then this is if there is happen to be a resistor here. And then usually this is a VL. Okay, this is VL. And then this is VZ. Okay, so first you assume that the Zener diode in open circuit. So it means that this Zener is in an off condition. So first assume that this Zener is off condition, and then you determine what are the value of VL, okay, across the Zener diode. So if this VL value, okay, if the VL is bigger than VZ, okay, usually VZ is given to you, yeah. If the VL is bigger than VZ, then the Zener diode is on. Then only the Zener diode is on, and the circuit is closed circuit. Okay, but if the VL here is lesser than VZ here, so there is no regulation happen, so VL will remain its value. Okay, VL will remain its value, and the Zener is off. So it means at this condition, yeah, VL lesser than VZ, there's no regulation, so the Zener will not act as a voltage regulator. But if the VL is bigger than VZ, okay, VL is bigger than VZ, then the Zener diode is on, and at this condition, only the Zener will act as a regulator. So this is how you want to determine whether the Zener will act as a regulator or not. Okay, so let's look into a cases, yeah. First, the cases is fixed VS, which is fixed, the source is fixed. Okay, the source is fixed, and the resistance also fixed. Okay, source fixed and the resistance also fixed. So the applied DC voltage and the load resistor are fixed. Okay, both are fixed. So the analysis, first of all, determine the state of the Zener diode by removing. Okay, first of all, you need to remove this Zener diode from the network and calculate the across voltage, the resulting open circuit, and calculate the VL first. Okay, first of all, you remove the Zener diode here, okay, and calculate the value of VL. Okay, so once you remove the Zener diode, okay, V at the output equals to VL. So these are the formula where RL, the value of the resistance, will time with the value of the input source, voltage input source, over the RL here, resistor value, plus with the resistor here. Then you will get the value of VL. Okay, so VL, okay, VD output. Okay, output. So at this time, since that there is no Zener here, so V outputs is equals to VL. So once you get the value of VL, okay, so now you need to compare. If the value of the VL just now that you get bigger than VZ, if it is bigger than VZ, so it means that the Zener diode is on, is operating as a regulator. But if the value that you get just now is lesser than VZ, so the Zener diode means it is off, so there is no, Zener diode will not operate as a regulator. Okay, so there's no further calculation after that. Okay, so if you want to determine even if the Zener diode is on or not, first you have to calculate using this formula. Okay. Right, I hope this is very clear to you. Okay, and so next, once if the Zener diode now is on, okay, so now you can proceed with other calculation. So the applied this next after the Zener diode is on, on state diode. So now VL is equals to VZ. Okay, the voltage across parallel element must be same as, okay, we have learned before. Okay, in a parallel condition, this voltage is always same. So VL will be equals to VZ. Okay. So the Zener diode current is determined by Kirchhoff law, which is IZ here. This is IZ and this is IL. This is IR. Okay. So IZ here is equals to IR minus IL, because the current has been divided into two, right? So IZ is equals to IR minus IL. How to find IR? You can always use Ohm's law. V divided by R, you can get the value of currents at this stage, So next, the power dissipation. Okay, the power dissipated by the Zener diode can be calculated. Okay, after you get the value of the currents here, okay, you can calculate the power value by use these formulas. Okay, VZ times IZ, so you will get this power. Okay, so as I mentioned just now, if the diode is off, there will be no further calculation because we assume that the circuit is not is open circuit and there is no current flow. Okay, so for the fixed VS and RL, okay, fixed VS and RL, the main formula that you have to remember is this, because this formula will determine either the Zener diode is on or not. Okay, if it is on, then you can proceed to calculate others information. But if it is off, so no further calculation because the circuit is open circuit. Okay, so you can mention that there is no value for power dissipation or Zener currents flow because the circuit is open circuit. All right. So let's look in example. Okay, let's look for example. First of all, assuming the voltage VI is 200 volts, R here is 2 kilo ohm. VZ, the value is 50. And then what you need to calculate VL, IL, and IR if RL here is 300 ohm. Okay, so first of all, what you need to calculate? You need to calculate VL, right? So VL from the Kirchhoff law, KCL, yeah, kenapa tak boleh tulis? VL is equals to RL VI over RL plus R, since that we assume that this diode has been removed from this circuit. Okay, so RL 300 and then VI 200 and then 300 plus 200, then you will get 26.09 volts. Okay, so that is the value of VL. Okay, next IL. How to determine IL? How to calculate IL? Oh, I didn't try. Okay, so how to calculate IL? IL using the Ohm's law, VL over RL. So just now VL is 26.09. 26.09 divide with RL value. So you will get the value is 86.97 milliampere. Okay, next. Next for the IZ and IR. Okay, IZ and IR. Can you calculate now? Can you measure what is the value of IZ and IR? Okay, is it okay? Now you, since that you know that the value of VL, right, 26.09. So can you suggest? Can you guess what if this diode is open circuit or closed circuit? 26.09. 26.09. Oh, sorry. It is lesser, right? It is lesser than 50. So it means that this diode is not working. So yes. KCL is Kirchhoff law. KCL is Kirchhoff law. Kirchhoff law. Just a short form is KCL. Okay. So the diode is not working. So no further calculation for IZ and IR because the circuit is not there is no current flow since that the circuit is open. So the Zener diode is off. So no further calculation for IC and IR. Okay? Is that up until that is okay, right? R is 200 or 2K? R is 2K, 2 kilo ohm. 2000 ohm, 2 kilo ohm. Okay, 2 kilo ohm. Right? For this one is 2 kilo ohm. For RL, 300 ohm. Okay, two different value. Okay, up until now it's okay, yeah? So no further calculation needed because the VL value is lesser than the VZ value. Okay, so no further calculation for IZ and IR because no currents flow inside here. Okay, alright. Next, how to erase this? How to erase this? Okay, next, macam mana nak erase ni? Sekejap, screen. Erase. We can erase this on. Okay, next, yeah. For question number 2. For fixed and for this type of condition, yeah, fixed source and fixed resistance, please focus more because this will come out in your final exam. For other condition, it's just for your information je. It will not come out in your exam at all. Okay, alam tak lah. Okay, next. I use this and again. Okay, so this is 2000, right? Okay, next. With the same assumption as above for VI, which is VI 200 volts, and then VZ 50 volts. Okay, so this value is same. If the Zener current range is 5 milliampere, this is the maximum value it can go. Yeah, no. Allah. IZM. And then sorry, this is IZK. It should be more than 5 milliampere, and then it cannot be more than 50 milliampere kan. This is IZM. Okay, so this is the range current of Zener. Determine the new value of the resistor. What is the value of the resistor that will regulate the voltage VL to the Zener voltage VZ? Okay, note now the value of RL is 1.4 kilo ohm. Okay. Okay, for this question, okay, for this question, so as I mentioned just now, you need to know the VL first, right? So RL VI over R plus RL. However, RL 1.4 kilo ohm, VI is same 200 volts. Over R is not given, you need to find the value of R plus 1.4 kilo ohm. Okay, so this is the VL value, right? Next, in order for the diode to work, okay, okay, VL, okay, in order for the diode to work, VL should be same with the VZ. Okay, we assume, yeah, in order for the diode to work, VL should be same with VZ. Okay, but for VR value here, okay, VR value here, if you want to find the VR value here, is 200 should minus with this value of VZ. So you will get 150 how many? 150 volts kan? Okay, 150 volts. So you can, from here you can find the IR. So IR is equals to VR over R, right? But R is not, you didn't know. So from here, IR is VR, you already know, 150 over R. So IR, another information for IR is IZ plus IL, right? Another information, because R you cannot calculate, right? So IR is equals to IZ plus IL, sorry. So IR, okay, IR, if you want to calculate IZ, okay, IZ for the currents, okay, the minimum currents, since that it's given to you the range, right? The range of currents. If you want to make sure that there is a current flow inside here, the minimum of the current should be inside this at this area of IZ is 5 milliampere. So let's take the minimum value, yeah, 5 milliampere plus IL. How to find IL? Okay, IL, you can find IL since that this is a parallel, yeah, parallel. So the value here is 50. So here is also 50. So IL 50 over the value of RL. This is the Ohm's law, yeah. You will get, sorry, you will get 35.7. So 35.7 milliampere. Ni 7 eh? 35.7. Okay, 35.7 milliampere. So the value of IL 35.7 milliampere. Then you will, from here you know what is the value of IR, right? IR, you have to plus these two value of currents. So you will get the value of current is 40.7 milliampere. So by using this, now you can find the value of the resistor. Okay, you can find the value of the resistor where R is 150 volts divide with 40.7 milliampere. So you will get how much? 3.685 kilo ohm. So this is the final answer for the R. So the value of R is 3.685 kilo ohm. Okay? Is that okay? This is not a straightforward question. Is that okay for this? Enough time for you to write? Okay, first of all, again, you have to make sure at this condition, for this question number 2, yeah, this condition, they said that with the assumption of the regulator, yeah, regulates the voltage VL. So it means that this Zener is working. Okay, it will regulate the voltage VL. Okay, so it means that VL will be more or same with the value of VZ. But we cannot assume VL is same with 50, with VZ value. But in our mind, we know that VL now is working. VZ now is working because it say regulates the voltage. So in order for the VZ to work, yeah, for the VZ to work, the currents, the minimum currents should flow inside VZ is 5 milliampere. Okay, so this is the minimum currents that should flow inside VZ for VZ to work. So the total current flow here is IR. So IZ plus IL. So IZ, minimum current, 5 milliampere. IL you can find using Ohm's law because this is parallel, both of them is parallel. Since the value here is 50 volts, here also will be 50 volts. Okay, so 50 volts divided by 1.4 kilo ohms, you will get the value of currents, which is 35.7 milliampere. So by adding IZ and IL together, you will get the value of IR, which is 40.7 milliampere. Once you get the value of IR, okay, once you get the value of IR, now you can find the value of R. Since you know the VR value, okay, VR value is 200, yeah, 200 minus 50, okay, 200 minus 50 because there is a 50 here. The VZ, the diode drops here, yes, 200 minus 50. So the value of VR is 150. So now you know already the information for voltage of VR and also the currents for VR, and you can find the value of R. Okay, so the value of R is 3.685 kilo ohms. Right? Why not substitute 50 volt into first equation at the left? I can't understand what you're saying. Why not substitute 50 volt into first equation at the left? Which left? Can you explain your questions? Why we cannot substitute 50 minus 50 with what? 50 volt as the VL. Okay, why we cannot assume the 50 volt as VL? Okay, why we cannot assume? Because in order for the VZ VL value, okay, VL value, why we cannot assume as 50? Because VL value, it can be more. Okay, in order for the VZ to operate, the condition or the syarat the condition is to VL should be bigger or same with 50. Sorry, not same. We cannot assume as same because VL should be bigger or same as VZ. So it is very wide range. So we cannot take as VL as the 50 because we don't know if it is what is the value, what is the exact value. Okay. But others information is very exact because this is 50 volts. This is also 50 volts. Okay, and then for the IZ to work, for the VZ to work, the minimum current is 5 milliampere. So that is very exact. I mean, that is very confirmed. But for VL equals to 50, that is not confirmed. Okay, because the VL value can be bigger. Or this one, yeah, this one, yeah, the one that I showed to you, left side. So this left side, I just want to inform to you that for first of all, you need to this is the information for VL. So for you to find VL is 1.4 kilo ohm times 200, and then R plus 1.4 kilo ohms, right? But you don't know what is the value of R. You don't know what is the value of VL. So for this equation, you don't know two things. You don't know. Okay, but once you know already the value of R, 3.685 kilo ohms, now you can calculate what is the value of VL. Okay, so if the questions continue, what is the value of VL? Okay, now you can continue with this left equation where the R is 3.685 kilo ohms inside here. Okay, so this is just for you to inform to you the basic equation just now. Why we cannot substitute 50? Just now, that's why I mentioned just now. Why we cannot substitute 50 as VL? Because VL has a very wide range of value. The minimum is 50. Okay, for this VZ to work, but we don't know if it is exactly 50 or not. But we know the exact value of minimum currents for VZ is 5 milliampere. Okay, so for at this stage, at this 5 milliampere, at this stage of 5 milliampere, the minimum current for VZ, it is not sure yet that the value of VL is 50. Okay, it might be the value of VL slightly bigger than 50. Is that okay? Is that okay? That's why we cannot assume that VL as 50. Right? So please be careful, yeah. VL, this is only for this, yeah, this one. Okay, this is only the condition to Zener to working for you to assume it is work or not. But the value will not be exact at 50. Okay, the value will be exact if you know what are the currents value here. Okay, what are the currents value here? Okay, if you try 3.685 include inside here, you will get the value of exact VL then. Okay, with the minimum currents of Zener. Okay. I didn't try to calculate. Maybe you can try later on. What's the value? Okay. So I hope for this fixed VS and RL, please focus on this more because this will come out in your exam, in your final exam. There will questions about this. Okay, questions for fixed VS and variable RL, they will not be tested inside your exam at all. So this is just for your information. Okay, so this is just for your information for you to know lah. Okay, for your knowledge. Okay, so fixed VS and variable RL. So the maximum and minimum value of RL will determine if the Zener diode can regulate the output voltage. Okay, so this value, the minimum and maximum value of this resistance can only be calculated if the Zener here is work. Okay, if the Zener here is on state. Yeah, so the changes in RL must keep the Zener current within IZK and IZM. So outside this range of Zener is not regulating and off. Yeah. So by taking the KCL, Kirchhoff law, the minimum and maximum load current is IL and IL minimum and IL maximum are given by IL minimum equals to IS minus I and IL maximum IS. Apa dia? Kenapa dia hilang? Yeah, IL maximum, IS, IZ minimum. Wait, Why it is lost here? I check. Sometimes maybe because of the formats is different, so that's why it's lost here. I check why it is lost. This is fixed VS and variable RL, yeah. IL minimum, IZ maximum. Sorry, so this is lost here. IZ here is IZ maximum. Wait, I share to you the exact screen. Because before I'm using different computer, and this is different computer. Yeah. I didn't know. Wait, yeah. VL become exact 50. Is there any chances VL become exact 50? I'm not sure. It depending on what is the minimum value for the currents in Zener diode. Okay, so there is a chances the VL become exact 50, but usually it will not become exact 50 because the value, depending on what is the minimum value of currents flowing inside the Zener diode. Okay, Zener diode, right? Okay, I want to show to you the exact formula because this is lost here. QU OTC,はい、QU OTC すると、ちょっと待ってね。これが、no, discard. Okay. Present a window. Now it's supposed to be this window. Wait, yeah, because this lost here. Yeah. I think this one. Okay. Am I sharing? No. I think this one. QU. Okay, can you see this slide now? Wait. Okay, please look at the slide now. Okay. So here is the exact value of the exact formula. Okay. Later on, I will put this inside your e-learning website again. Yeah. Because in your paper also, yeah, it happened to be like my slide, is it? Or it's can be seen inside your paper. If not, I need to revise again your cannot sensei. Okay, so I will revise again inside your e-learning. Okay, for this but this will not come out inside your exam, but just for your knowledge lah. So IL minimum, okay, equals to IS minus IZ maximum. Okay, for you to measure the minimum of currents that flow at this resistance is the IS here, okay, minus the maximum value of currents that flow inside the Zener diodes, yeah. And for you to measure the IL maximum, okay, the maximum value of resistance currents that flow inside the resistance, here is IS minus the IZ minimum, the minimum value of currents that flow inside the VZ here, okay. So the minimum and maximum load resistor can be calculated by, yeah, this is Ohm's law, okay. So minimum value IL maximum, okay, divide with the voltage will give you the minimum of resistance, yeah. And for you to calculate the resistance, the maximum value of the resistance, you should divide with the minimum value of the currents flow inside the resistance, okay. So this is the fixed VS and variable RL. And later on, you can also see the example that I already gave to you and the example of the solution. Okay, so this is the example of the solution. I think we don't have to discuss this because this will not come out inside your exam, right? But the solution also is not included inside your handout, right? I just remember, aduh, what I forgot to put this one. So I will give again later on your e-learning. Okay, check your e-learning again after this. I will include the solution for question example fixed VS and variable RL. Okay, and then next, okay, next is variable VS and fixed RL. Yeah? Variable VS and fixed RL. So the changes in the input source. Okay, now the input source voltage is regulating. It means, sorry, not regulating. Now the input source voltage is variety. Okay, it can change. Yeah. So to regulate a fixed load load is referred to line regulation. So now it is line regulation, no longer load regulation. For fixed VS and fixed RL, and also fixed VS and variable RL, we call that regulation is a load regulation. However, for this kind of situation of circuit, yeah, where the variable, the source input is variable and the load is fixed, it is called as line regulation. Okay, so the Zener voltage will maintain a constant DC voltage across the load as long as the variation in the source voltage keep the Zener current within its minimum and maximum. So this is the this is much more complicated. That's why it will not come out in your exam. Okay, so these are the example of the formula. Yeah, formula example. And you can also see the example. I think I also not include the solution inside your notes. Later on, I will give again, okay, inside your e-learning, and then you can check it again, yeah. And what, yeah? Okay, that's all. That's all for today. And inside your notes, there's also other applications, right, for Zener, which is it can be used as it can be used for limit voltage swing. So this as a clipper. So this is just other information, additional information for you. Okay, for where we can apply Zener diodes. Okay, so these are extra knowledge for you. Okay, but if you want to read more or read further information, you can just Google about this clipper and all those things. Yeah, and again, for things that I want to inform to you for your test, we haven't done the quiz yet. Yeah, maybe I will inform to you. I think I want to do the quiz around next week, but around next week on Tuesday. I think quiz can be done anytime, right? If not inside the class time is also okay, right? Because you can just email to me and send to me the answer for your quiz, because if quiz is only around 10 to 15 minutes like that. So I haven't decided yet when I want to do your quiz, but it will be around next week. Okay, inshallah, around next week for your quiz. But for your test, yeah, for your test, the lecturers has been decided to make your test on 22 of April. Okay, please record, yeah, your test will be on test 22 of April. It's on Ramadan month. Sorry of that. Test on 22 of April at 5 o'clock. Yeah, 5 o'clock. Okay, 5 p.m. 5 p.m. So after you complete your test, you can happily have your break. Fast break. Yeah, you can break your fast at 5 p.m. Okay, so please be ready lah. You can have your iftar after that freely. It is around 1 hour, 1 hour and a half. Your test. 1 hour 15 minutes around that. Okay, 1 hour 15 minutes. Okay, the plan will be around that times lah. So please note it. Yeah. So the test will be on 22 April, which is on Thursday, if I'm not mistaken. On Thursday, okay, Thursday, 5 p.m. All right. So the range of your test until half wave rectifier. Okay, half wave rectifier and also Zener. Okay, Zener fix. Yeah, I think fix will be asked during your test, but Zener, the circuit analysis will be asked during your exam. but during your test, they will ask about how to calculate the power dissipation, how to calculate the that we learned just now lah. Apa tu? How to calculate the apa tadi yang kita belajar tadi? Ingat lah. Power derated, okay, how to calculate the impedance, all those basic knowledge about Zina. Okay, and if there is other further information about your test or your quiz, I will inform to you in the WhatsApp group. Okay. All right. So anything that you want to ask? Any questions? Oh, today our class is very long, yeah. Usually we finish earlier. Any questions? Okay, not yet. Okay lah. Yang penat lah kan. So if any question, you can just freely email me or message me, text me. Okay. Thank you for today. Okay, for those who doesn't have your breakfast yet, please have your breakfast. And thank you. Assalamualaikum.
Thank you, Doctor.
Welcome.